We want to welcome you to another statistical topic. Before I get started today, of course, politicians will say election have consequences. I also want to believe assignment, tests, and exam also have consequences. Of course, I want to believe you see your results for assignment one, you see your grade for assignment one. And if there is anyone that is struggling in this class, if you get stuck, like I said, you reach out to me. And if you are not satisfied with the kind of grade you get, of course, you can complain to me. You need to reach out to me. So, of course, I'm going to look at it because my TA handle the grading in case there's anyone who, because I actually want a situation where every student will be graded fairly. Okay, so I'm going to go into the topic of the day. Statistics is like a story that goes on and on and on. So today's topic is application of central limit theorem. Of course, you've been introduced to central limit theorem. It's very, very crucial in statistical analysis. So the outline today, I'm going to have a review on the law of large numbers. I'm also going to have a review on the central limit theorem before I go into the real-world application of central limit theorem. There is a connection between the law of large number and central limit theorem, and that is the reason why I'm going to have a recap on the law of large number. So I'm going to start with the law of large number. You know, in the law of large number, of course, the idea behind the law of large number is when we actually choose a sufficiently large sample, we expect the sample mean to converge to population mean. And of course, you know, we got two different types of the law of large number. We got a weak law and we got a strong law. You know, the weak law is actually going to talk about convergence in probability because we expect the sample mean to converge to population mean, okay, within a certain number that we call epsilon. And why for the strong law, of course, you know, that handles what I call absolute convergence, okay? Absolute convergence, and we call that convergence almost surely. And the takeaway, you know, with the law of large number is that even though we are trying to estimate the unknown population parameter and we take a sample, when we take a sample and we obtain a sample mean, the sample mean becomes a random variable because you compute the mean from sample. So definitely, if 1,000 researchers should compute this, you know, mean from sample, they're actually going to have different results, and because of that, the mean becomes a random variable. And what we're trying to say, when you take a very large sample, we expect the sample mean to converge to population mean. But let me tell you this: you cannot conclude central limit theorem on law of large number. I'm going to say that again. You cannot induce or conclude the central limit theorem based on the law of large number, because the law of large number only talk about the convergence of sample mean to population mean. But when you talk about the central limit theorem, on the other hand, you know, when sample size goes up, okay, the distribution. We are actually talking about the probability distribution of the population of interest. Okay, even though the probability distribution of the population of interest is not normal, but we believe when we take a reasonable large sample, we expect the probability distribution of the sample mean, okay, to follow normal distribution. Okay, so let me tell you this. Do you know that if the probability distribution of the sample mean now follow normal distribution, we can also conclude convergence of sample mean to population mean on central limit theorem. Because I demonstrated the other time in this class where I started with an exponential distribution with a parameter beta equal to 1, and you saw in the end there was a convergence from, the sample mean converges to population mean. Not only that the distribution converges to normal, even the sample mean converges to population mean. You saw the convergence around 1. So which means we can conclude the law of large number from the central limit theorem. But we cannot make a conclusion about whether the distribution of the sample mean will convert to normal based on the law of large number. I'm going to repeat myself. We cannot conclude that the distribution of the sample mean will converges to normal using the law of large number. The only thing we can say with the law of large number, under a sufficiently large sample, the sample mean will converge to population mean. But with the central limit theorem, we can actually conclude the two. With the central limit theorem, we can conclude that the sample mean is going to convert to population mean, and not only that, the distribution, the probability distribution of the sample mean will converge to normal. And that is the reason why central limit theorem is a cornerstone of statistics. Okay, the central limit theorem is a cornerstone of statistics. In fact, central limit theorem is a justification of the law of large number. I'm going to say that again. Central limit theorem gives us further illustration of the law of large number, and of course the bedrock in any statistical analysis. Okay. Now, mathematically speaking, if I want to talk about the central limit theorem, of course, I have a y1, y2 up to yn. They come from the same distribution, and they are independent. Okay, it doesn't matter whether they follow normal distribution or not. If they don't follow normal distribution, the only thing that, apart from having a large sample size, is the requirement that the mean and the variance has to be finite. The moment the mean and the variance of the underlying distribution of a random variable is finite, then if sample size of is sufficiently large, of course the central limit theorem is going to apply. Now, the central limit theorem, I wanted to take a look at what I'm going to do right now. The central limit theorem applies to the sample mean and also applies to the sum. There's a difference between the two. When I'm talking about the convergence of the sum of a random variable, the sum of a random variable is going to be summation y, right? What does it mean? Okay, what does it mean? The mean is going to be n mu. You remember when I have y1 plus y2 up to yn, and I take the expectation of the sum, what am I going to have? I'm going to have expected value of y1 plus expected value of y2 up to expected value of yn. And what am I going to have if the expectation is the same? It's going to be n mu, right? That would be n mu. So n mu is actually, okay, n mu, this guy, that is the mean. of the sum of random variables that are identically distributed. They are identically distributed, and that is why they're going to have the same values of mean. So if you have n, if your sample size is n, that's going to be n mu. If your sample size is 5, that will be 5 mu. Does that make sense? Now, what about the variance? Oh, the variance of y1 plus y2 up to yn, okay, because y1 up to yn are independent, there's not going to be covariance. The covariance will be 0. And now what we're going to have is the summation of variance, right? Going to be variance of y1 plus variance of y2 plus variance of y3 until you get a variance of yn. And all these variances, take a look at this guy. The variance of yi equals sigma squared. Variance of y1 sigma squared. Variance of y2 sigma squared up to variance of yn. What would be the variance? The variance would be n sigma squared. Does that make sense? That would be the variance of the sum of random variables. Now, if the variance of the sum of the random variable is n sigma squared, if it is this guy, n sigma squared, what would be the standard deviation? The standard deviation is going to be the square root of that. Right? That was why we got this guy here. Do you see that guy? When you take the square root of this guy, this is going to be square root of n, the square root of sigma squared. Look at that. So the central limit theorem apply to the sum of random variables. And not only that, also apply to the mean. Take a look at that. It applies to both. Okay. Now what we're trying to say is this. If you are working with y1 up to yn that come from a distribution other than normal, if we make this attempt, okay, we want to focus on we want to figure out the CDF, the cumulative density function of the distribution. You know, it's always, you know, an uppercase, less or equal, right? Now at n tends to infinity, that CDF will converge to the CDF of a normal distribution. That's what that guy is talking about. Any question about that? I'm going to say that again. If UN, the UN may be a sum of random variables. The UN will be a sample mean, could be a sample mean. The UN could be proportion. Okay. The UN could be certain statistic of interest. Okay. If the UN comes from a distribution that is not normal, okay, what we're trying to say, the CDF of that UN from that distribution will converge to the CDF of a normal distribution, provided the sample size is large. We've demonstrated that the other time. That is just the theoretical aspects. Now, this is the graphical demonstration of what I'm talking about. You started with a skewed population. What do I mean by skewed population? The probability distribution of the population, you know, from where the random sample is going to be chosen is skewed. It's asymmetric. It's not normal. Take a look at that. But you know what? When you take a sufficiently large sample, okay, the distribution of the sample mean will be normal at the end of the day. That's what we mean. That's what central limit theorem actually talking about. That's a graphical interpretation of that. In the last class, I think I actually walk you through, the theoretical development of central limit theorem. Okay, now I want to go into applications of central limit theorem. Before I come into this, you know, this is going to be like step-by-step implementation of central limit theorem in real world. But before I get into this, I remember the other time I demonstrated the significance of law of large number in real life practical situation. Central limit theorem also has application in real life practical situation. And of course, that is what I want to demonstrate now. Okay, that is what I want to demonstrate now. Now, let me just give an example in business. Let's say in business, we want to apply central limit theorem in business. What are we going to do? What are the steps involved? Number one, I need to define the problem. What problem do I want to solve? I'm going to give you an example now. The problem could be, maybe we're into production and we actually want to determine the average weight of our products. Okay? And of course, every company, they have what I call a target value, like what they are targeting, right? And they will actually want to see whether there's a conformance between what they produce and what they actually propose. What they propose, the value of what they propose is more or less like a parameter, like a population mean. Okay, now the sample mean, if they want to conduct a study, of course, they are not going to investigate every item they produce. They don't have time for that. They are limited by budget, and because of that, they're going to take a sample, right? Now, number one, we define the problem. The problem is that we actually want to know the average weight of our products. Any question about the definition of the problem? Okay. Number two, determine the sample size. We have a way to determine sample size in statistics, depending on the numbers of error we want to tolerate, okay, the level of confidence, and so on like that. Okay, we have a topic designated for that we call sample size determination. But you know what? We don't need to go into that rigorous way to determine sample size. We can actually follow the law, and we can follow the central limit theorem if we want to do this. Okay, and we advise that we vary the sample size. Of course, we already know the population mean. Okay, the population mean is what you propose to produce, the weight. Okay, that is the anticipated weight, right? Okay, now you try a small sample, you try moderate, you try large. Of course, we know that I told you the rule of thumb the other time, at least story, right? To be large. Now, what I'm going to do, I can decide to take at least story. Okay, let's say in the step 2, the sample size is story. Just assuming that. Then in step 3, I'm going to collect the data. How am I going to collect the data? I'm going to take a random sample of story, okay, from the production lot. Then I'm going to weigh them. I'm going to record the weight. Okay. Now, when I record the weight, I'm going to do repetition. You remember the other time? I'm going to replicate, like, I'm going to visit that population lot severally. Okay. And I'm still taking a sample size of 30. In the first occasion, I take a sample size of 30. I found the average. I record that. I go back into, and I'm going to be sampling with replacement. Before I go for the second one, okay, I will need to replace those ones, because don't forget, I want to be choosing at random. I'm going to go, a second time, I'll select 30 again, calculate the mean. If I go 1,000 times, you remember, if I go 1,000 times, I'm going to have 1,000 means, right? And that is what you see. Calculate. After calculating the sample mean, repeat sampling. Repeat sampling is when I revisit the population more than one time Okay, we did that the other time when I was walking you through simulation. Okay. Now, after that, we're going to have, like, if we visit the population 1,000 times, we're going to have 1,000 means. Okay. Now, provided the sample is sufficiently large, what is going to happen? The means, the 1,000 means will follow normal distribution. And if the 1,000 means follow normal distribution, then the expected value of the sample mean, which is the mean of the means, will give us the population mean. That is what this guy is talking about. Then, based on the means, we calculate the standard deviation. The standard deviation of the means is called standard error. The standard deviation of means is called standard error. Then we apply the CLT. That's how we do that. Okay. Now, I got this example from the textbook, and I wanted to, sit back and ask questions where necessary. Here, achievement test scores of high school seniors in a state have mean 60, variance 64, and a random sample of n equal to 100 students from one large high school had a mean score of 58. Is there evidence to suggest that this high school is inferior? Calculate the probability that the sample mean is at most 58 when n equal to 100. Let me tell you one of the significance of the central limit theorem. Like I said, is from what I call is a cornerstone of statistics. We use it in testing hypotheses. Idea of the central limit theorem is used in testing hypotheses, in constructing confidence interval, and not only that, even in simulation study. You remember I demonstrated that the other time in the last class, the simulation study. Now, what do you think we want to figure out here? A population actually has a mean of 60 and a variance of 64. And you choose a random sample of 100, okay, from one large high school, and you have a mean score of 58. Of course, everybody knows that 58 that happens to be the average for their high school is less than the population mean. Now, the question now is, does that suggest that the high school is inferior in terms of, when the fact that the mean is less than the population mean? Do you know another way we can actually say that is to see whether it is possible that that particular sample is from that population? Let me tell you another thing, another way I can interpret example 7.8. Example 7.8 can be interpreted, in terms of testing hypothesis, where we're actually we're still going to talk about it, but I know you've heard about hypothesis formulation before, where you're going to have the non-hypothesis. Here, mean the hypothesized value is actually 60, okay, against the alternative hypothesis. Can somebody tell me, for extra credit, what is going to be the alternative hypothesis here? When the mu, okay, what is going to be the alternative hypothesis?
That the mu is less than 60.
Exactly. Send me a message for extra credit. Good job. That the mu is less than 60. This is what we want to test. If you accept the alternative here, you are actually concluding that that school is inferior. And in hypothesis testing that we're still going to do, or the one you've heard about before, if we want to investigate this, we need a p-value. Oh my God. The p-value is what we actually want to find here now. The p-value is the probability, okay, that the sample mean is at most 58. And let us see, by central limit theorem. By central limit theorem, we want to find this. For your information, we don't know the distribution. We don't know what the distribution may be normal or not. We're not interested, right? But what we can see here is the sample size is large because the rule of thumb suggests at least 30, right? And this is 100. Now, if that happens, then I will be able to, interpret that as this, where the sample mean as the mean of mu and the standard deviation of sigma over root n. Okay, now by that we believe our z is going to follow standard normal distribution. You know why? N equal to 100, CAT applies because we got the rule of thumb. The rule of thumb is at least 30. Okay, now in the end, you're actually going to you want to find the probability of z less or equal to negative 2.5. This is where we make use of statistical table, or you can make use of R. Here it's going to be P norm of negative 2.5. That will give you is 0.0062. Oh my God, when the probability is 0.0062, that is extremely small. So which means, okay, that very school is not likely to come from the population. The 58 that you got is not from that sample size is assumed not to come from a population with a mean of 60. Okay, well, the conclusion is going to be that school is inferior. Let's look at it from hypothesis angle. From hypothesis angle, we're actually going to take this as a p-value, right? Oh, when the p-value is less than a level of significance. For this, you guys have done statistics before. We are the lower level statistics, because in the lower level statistics, if you conduct hypothesis, we're actually going to compare the p-value with the level of significance. The level of significance, a standard one used to be 0.05. When the p-value is less, at the level of significance, you reject the non-hypothesis. Right now, take a look at that. Is it not less? It's less than 0.05, which means if I want to go by the way of hypothesis, I'm rejecting the non-hypothesis. Rejecting the non-hypothesis actually means you're going to conclude in the favor of the alternative. Any question? And that was why I have this conclusion here. Look at interpretation. Because this probability is so small, it is unlikely that a sample from the school of interest can be regarded as a random sample from a population with mu 60 and sigma square 64, and the evidence suggests the average score for this high school is lower than the overall average. We can use this when you want to compare the performance of a school to the national. We live in a world where we always want to compare. Because if you really want to stay relevant in this world, you need to compare yourself with the standard. You want to be better than the standard, right? That is it. Any question on this? Any question? Any question? Okay. I'm going to go to example 7.9. All these examples actually, they were extracted from the textbook. Okay. Now, the service times, okay, for customers coming through a checkout counter in a retail store are independent random sample with mean 1.5 minutes and the variance 1.0. Approximate the probability that 100 customers can be served in less than 2 hours of total service time. If you take a look at this question, this is centered on the sum of random variable, not on the mean. I told you the other time, the idea of central limit theorem can be used for sample mean and also for the sum of random variable. Now, you have y1 up to y100, IID from a distribution that you don't know. It may not be, in fact, it's not likely going to be normal, okay? But there's no problem with that, okay? Now, we want to find the probability. We want to find the probability that summation y will be less or equal to 120. Okay. Do you know I can move from summation y to the mean? You know, when I divide summation y by the sample size, that will give me the average. What was the average here? What was the sample size here is 100. If I divide both sides by 100, of course, I'm actually going to get this guy now. It's going to be y bar less or equal to negative 1 point. I mean, less or equal to 1.2. Any question on that? Any question? You are good, right? Okay. Now, but I know that the expected value of y, okay, the expected value of y is 1.5. You know, expected value of y, okay, is 1.5. And you know what? Expected value of y is also going to be equal to the expected value of y bar. They're all going to be equal. Okay? And that was why you actually see this. Okay? So that is why you actually see that. Okay? Expected value of y bar is also going to be the same as the expected value of y. Okay? Now, what about, and the idea of central limit theorem can be used here because of the sample size. Okay, it's at least story. Now, what about the variance? If I know the variance of y, then I will be able to find the variance of y bar. What was the variance of y? You know, you're giving a variance 1.0. If the variance of y, don't forget, the variance of y is sigma squared, but the variance of y bar is sigma squared divided by the sample size. And that was the reason here why you see 1 divided by 100. The sample size is 100 here, right? And of course, the variance of y bar is going to be 1 over 100. Then from there, you can find the standard deviation of y bar, taking the square roots. That's going to give you this guy. The moment you have the expected value of y bar, you got the standard deviation of y bar. And if the sample size is at least 30, then the central limit theorem applies. Then I can now go into my z formula. Okay, so that is, so I'm right here now. Y bar minus the expected value of y bar divided by the standard deviation of y bar. I'm just going to plug in the values. I can apply central limit theorem because of the fact that n equal to 100. How large is the large is at least 30, according to the rule of thumb. 100 is sufficiently large. Now, this apply, we can now see that z for approximately follow normal with a mean 0 and a variance 1. Then if I want to find the probability, don't forget what I want to find is the probability of the summation y less or equal to 120 is the same as the probability of a y bar less or equal to 1.2. Okay? So all what I'm just going to do is to plug in 1.2 in that. Look at that at the end. I'm actually going to have the probability of z less or equal to -3. I can make use of my statistical table. Or use a coding now. I can just write p norm of -3. And of course, the final answer is going to be 0.00135. And that probability is very, very small. Then I'm going to have this as interpretation towards the probability that 100 customers can be served in less than 2 hours is approximately that. And this small probability indicates that it is virtually impossible to serve 100 customers in only 2 hours. Okay? Virtually impossible because the probability is very, very small. Any question? Any question? You're good, right? Like I said, do not hide your feelings. you have any question? If you get stuck, you pay for the service, please direct your question to me. I want to go into another question now, but this time around, we're actually going to be dealing with the two independent population that we can also call two independent groups. The one we'll be working on is just one population, but right now, we want to focus on two populations, and that is the reason why we're actually going to be choosing a random sample from the first population and from the second population. Now, suppose that x1 up to xm and y1 up to yn are independent random samples with the variable xi normally distributed, you've been told here, with the mean mu1 variance of sigma 1 squared and the variables I normally distributed with the mean mu2 and the variance sigma 2 squared. The difference between the sample means, that is x minus y, okay, is then a linear combination. Give me 1 second. Between the sample means, I think there should be a bar here and a bar here. When I'm talking about sample means, you can correct that, okay? Now, is then a linear combination of n plus n normally distributed random variable. Of course, you know, if x is a random variable, y is a random variable, x minus y is also a random variable. X plus y, random variable. Okay, so that is going to be normally distributed. So, what is the question? Find the expectation of x bar minus y bar. Find the variance of x bar minus y bar. This is like the point you're trying to find the estimate of the difference. And the second one, well, of course, when you get the average of the difference, because the average of the difference is a random variable, how can you rely on the average? Because you are taking a random sample, the difference of the average is going to vary. Then to tell on the reliability of that, then we need the variance of that. Okay, and after that, C said, suppose sigma 1 square is 2, sigma 2 square is 2.5, and the sample size that you choose independently from the two populations is the same. Find the sample size so that the difference will be within the one we've been doing. We only be focusing on one variable at a time. But right now, two variables, okay? The difference of the two variables will be within 1 unit of the mu1 minus mu2, because this guy here is the true mean difference. That is the one we are anticipating. The expected value of y bar minus x bar minus y bar is just going to be an estimate. Now I'm going to start with the first one. That will be super easy to do. Okay, you know, this guy here can be written as, you can distribute that, right? Minus expected value of y bar, right? You know the law we're using, okay? And you've been given expected value of x. Expected value of x bar is the same thing as expected value of x. Expected value of y bar is the same thing as the expected value. And so this guy here, okay, you've been given that to be mu1. Don't forget, they gave you expected value of x in the question, okay, to be mu1. Then the expected value of x bar is also going to be mu1. Okay, in the question, the expected value of y, whatever y, whether yi, whether y1, y2, or whatever. Okay, so this guy will be the same as mu2. So what would be the answer to that one? The first question is going to be mu1 minus mu2. Any question? Just mu1 minus mu2. So it's going to be mu1 minus mu2. Now, going to the second question, this guy. You've been told that X and Y are independent. Okay? If X and Y are independent, then X bar and Y bar will also be independent. I'm going to say that again. If X and Y are independent, because we've been told, take a look at the question. They are independent random variables. So the expectation, the X bar and Y bar will also be independent. And this guy can be, it is going to be equal to the variance. If I want to, give me 1 second. If I want to rewrite that guy, it's just going to be V of X bar, okay, plus V of negative Y bar, okay. Of course, the V of negative Y bar is also V of Y bar, because the negative is like a -1 squared, okay? And the covariance is just going to be 0, okay? Now, because we're told X and Y are independent, X bar and Y bar will be independent. And this guy is going to be sigma 1 squared divided by M plus sigma 2 squared divided by N. You're done. Okay. Now, going to the next question. Suppose that sigma 1 square equal to 2, sigma 2 square equal to 2.5, and M equal to N. Find the sample size so that the X bar minus Y bar would be within 1 unit of that with the probability 0.95. Take a look at this. This is a mathematical interpretation. Is there anyone who doesn't understand how I interpreted it to be that? Because if this guy here is a random variable, then this is the mean. That is the mean. Okay? So the probability of the absolute value will be less or equal to 1. Okay, it's equal to 0.95. That is the mathematical interpretation. If I want to remove the absolute value, okay, if I want to remove the absolute value, mathematically speaking, I'm going to have this guy. Then that is going to lie between -1 and +1. Any question? Okay. Now, what I'm going to do right now, I will apply, getting this z-score. Okay, we've gotten the variance of the difference to be this guy divided by M plus this guy divided by N. And we've been told M equal to N. I can just have sigma 1 square over N plus sigma 2 square over N. And you'll be given the values of sigma 1 squared, the variance of the first one, the variance of the second one. By the time you plug that in and you find the square root, you're actually going to find yourself here. Okay? And when you find yourself there, you want to find the probability of z less or equal to that minus that equal to that. By the time you do what you're supposed to do, okay, you're going to continue to go like that, and you're going to end up getting the sample size. We always, even though if you see what I have right now, mathematically speaking, if I want to round this up, it should be 17. But in statistics, when you are dealing with the sample size determination, we normally round up. Okay? That's why I said at least 18. Any question on this? Okay. I want to go into the next question. A pollster believed that 20% of the voters in a certain area favor a bond issue. Is 64 voters are randomly sampled from the large number of voters in this area. Approximate the probability that sample fraction of voters favoring the bond issue will not differ from the true fraction by more than 0.6. Here, the parameter of interest is proportion. The one we've been dealing with is, you know, the sample mean, and it is the mean. The objective is to find the probability. This is the solution. You want to find the probability that a sample fraction of voters, you know, favoring that will not differ from the true fraction by more than 0.06. You know your hand. Your sample size is 64. And your sample proportion, you know, I mean, let P be the population proportion is 0.20, we know which is already given. A pollster believe 20%. That's a population proportion, 20%. Okay. Now, this is how you can interpret that. Is there anyone who doesn't understand that? When you are dealing with proportion, it's always y over n minus p. Please take note. Y over n minus p. That is for the proportion. Less or equal to that, if you remove the absolute value, it's going to be that. And let me tell you this. When you are dealing with proportion, your mind should be on Bernoulli. Bernoulli. What is the variance in Bernoulli? Is P into 1 minus P. If a random variable Y follow Bernoulli, okay, what does it mean? P, right? Expected value of Y for Bernoulli is P. What is the variance of Y for Bernoulli? Is P into 1 minus P. If I now want to talk about Y bar, you know, I know that if Y follow Bernoulli, okay, Bernoulli with parameter P, you have to notice expected value of Y, okay, equal to P, okay, the variance, this is from statistical theory, the variance of, why is it Bernoulli? Because we're talking about proportion, right? The variance of Y, okay, is actually P, right? 1 minus P. Now let's take a look at this. If the expected value of Y equal to P, then the expected value of Y bar will be P. If the variance of Y equal to P into 1 minus P, then the variance of Y over n will be P into 1 minus P divided by n. What would be the standard deviation? And that was why you got this guy here. Oh my God. Take a look at that. Okay? Now, you're going to find yourself here. When you find yourself here, by the time you simplify the denominator and you simplify the whole thing, oh my, I'm afraid you're going to find yourself here. Super easy. Where you're going to fall. First, work with the maximum one minus the minimum one. You can check from statistical table here, or you use our software. It's going to be P norm of 1.2 minus P norm of negative 1.2. In the end, you're actually going to get this. This is the end of this statistical party. Is there any question? Any question? Make sure you all stay safe and have a lovely day. See you on Friday. Oh, go ahead. Is it on? I record it, but my headset is having issue. So what I'm gonna do, if I watch this recording, and if it is bad, I promise I'm gonna record it tomorrow. I'll record it on Zoom, then I will publish that. I promise. You are